Hi, I'm Paul. We're doing Leetcode must know interview questions, and today's challenge is course schedule. Uh, Medium rating, there are a total of num courses. Well, okay. What is num course? We'll take a quick look at the method signature. The input is num courses, an integer. That's the number of courses that you have to take. And then there's a two-dimensional array of integers indicating the prerequisites. Well, this will make more sense when we look at an example. So you have a certain number of courses you have to take. These are labeled from 0 to num courses of -1. And you have an array of prerequisites where prerequisites I equals A sub I, B sub I, meaning that you must take course B sub I first if you want to take course A sub I. For example, the pair 0, 1 indicates that to take course 0, you have to first take course 1. Return true if you can finish all courses, otherwise return false. These examples to me are too simple to be really useful. I don't know. Yeah, number two is better. All right, so prerequisites. Prerequisites is going to be an array of two-element arrays. Each two-element array will indicate that the second element in the array, this representing a course, is a prerequisite for the first element in the array. So in this one, well, in this one, the first one, example 1, this is fine. You have two courses, 0 and 1. You have to take 0 before 1, so no problem. This one, it says before you can take 1, you have to take 0. Before you take 0, you have to take 1. All right, so that's not going to work. Let's look at the topics here. Depth first search, breadth first search, graph, topological sort. All right, so I think these are the keys here, graph and topological sort. What we want to be able to do is to detect cycles, okay? Detect a cyclic dependency among the courses, such as example 2, which makes it impossible to complete all of them. Okay. So here's what we're gonna do. Let's see. Well, what do I want to talk about first? Well, I mean, let's talk about what is a topological sort. Got that? Okay. Let's do this. Let's say we have a graph and we have a node here with a value of 4. This is a directed graph, meaning 4 is a prerequisite of 2, and 2 is a prerequisite of 1, and 3 is a prerequisite of 1. All right, well, a topological sort means that you sort the nodes in the graph such that any node with a dependency on another node will come after that node in the sort. Now 3 doesn't have any dependencies, so 3 can be anywhere. What would be a valid topological sort for this? Well, 3, 4, 2, 1 is fine. 4, 3, 2, 1 is fine. 4, 2, 3, 1 is fine. But let's change this up a little bit. And we'll take this off, and we're going to add 5 here. Okay, and do that. All right. Where do you want to start here? It doesn't really matter. Let's say we start at 4, and then 2, and then 5. Is that a valid topological sort? Well, it isn't, because 5 because 4 depends on 5. 5 is a prerequisite to 4. So the thing that is going to work for us here as far as the topological sort, we can do a topological sort. There's more than one way to do topological sorts, but we're not really interested in getting the topological sort. We're relying on the fact that any graph with a cycle, you can't do a topological sort. So we're going to try to do a topological sort, and if we can do it and get all the courses, then we'll return true. If we try to do a topological sort and we find that we can't do it, then we'll return false. Let's see, is there anything else that I want to talk about here? Basically, we're going to construct a directed graph or a digraph. Each node is a course. Each edge represents a directed edge from course B to A, meaning that B is a prerequisite for A. We're going to count the number of in-degrees or incoming edges for each node. So in that first example, the 3 node didn't have any incoming edges. That means we could take that right away. The way we're going to do it is to put it, we're going to use a queue for this, but if we put nodes with no incoming edges in a queue, dequeue it, and then look at what nodes depend on this node. And we can reduce the in degree of those nodes because we've satisfied the prerequisite. Now, if any node, if the in degree goes to 0, then we can put that node in the queue. And if we manage to remove all the nodes, then it's possible to finish all the courses. So let's look at an implementation. All right, the first thing we need here, is a data structure for the graph. And we're going to represent the graph with adjacency lists. That means, let me finish this. Graph equals new array list. So each element in the graph is going to contain, the indexes will correspond to the course numbers in the graph list, and each element will be a list of the prerequisites for that course. So let's do this. For int I equals 0, I is less than num courses I plus graph dot add new array list. All right. So that just sets up the graph. Initially empty. Each element has an array list. Each array list will contain the prerequisites for the course corresponding to that index in the list representing the graph. All right. I said we were also going to need this is an array in degrees equals new int num courses. All right, we're going to keep track of how many prerequisites, how many active prerequisites does each course have. Okay, now we're going to populate populate the graph, populate the in degrees array. So to do that, we got to go through the prerequisites input. So for each integer array, that's the 2-element array, prereq in, well, do I want to do that? You know what? I don't want to do it that way. Let's spell it out. For int prerequisites, prerequisites, the course is the first element. And the prereq is the second element. Okay? So we can say graph, get prereq dot add course. And that's not right. The parentheses has to go here. Okay. And it just occurred to me that I think I may have been saying this wrong as far as what the adjacency list represents. I think I've been saying that the adjacency list represents the prerequisites for the course. The adjacency list represents the courses for which the course is a prerequisite. So okay, like this. So we'll get the adjacency list for a course, and then we will add the course for which. Wait a minute. Then add the course for which the for which the prerequisite is a prerequisite. Oh gosh. And we have to increment the in degrees here. So in degrees for the course is going to be, we're going to increment that. All right. We need a queue to implement the topological sort algorithm. So we can use a deck for this. This will be integers. We'll call it q equals new array q. Okay. NQ, all the courses that don't have any prerequisites. In other words, the in degrees is 0. So we can say for int I think I have something like just like this. Let me just copy this. I know I can use some of it. For int I is num course I++. Yeah, that's about all I can use. We will say if in degrees I equals 0, q offer, we'll put it in the queue. All right. Now we need a counter. We need a counter for processed courses. Again, we don't want, we're doing a topological sort, but there's a possibility that it's not going to work in any case, we're not doing the sort because we want the sort. We're doing the sort to see if the sort can be done. And as we're doing it, we'll keep account of the courses that we're able to process. And if that number equals the number of courses, the process courses equals the number of courses, then we'll return true. All right. While not queue is empty. All right, while the queue is not empty, let's see, dequeue a course. Course equals queue.poll. And process courses, we can increment it because we got a course off of there. All right. Now we need to look at the courses for which this course is a prerequisite. So let's do this. For int neighbor in graph dot get course. This is going to be the adjacency list. Let's see. In degrees of neighbor just went down because we completed the prerequisite. All right. Now, if in degrees went, if in degrees went down so far that it's now 0, then we can queue it. Queue offer neighbor. All right. And success means that the processed courses equals num courses. Okay, that means we would be able to do a topological sort, meaning there's no cycle. So let's try it. Uh-oh, no, network error. I think it logged me out. Okay, hang on. All right, I think I'm logged back in. Let's try it again. Run. All right, accepted. That's the basic cases. Let's try the full test suite and submit. Okay, 7 milliseconds. Oh my God. Well, let me think about that. I mean, how could we speed that up? I mean, well, I don't know. There are more than one. There is more than one algorithm for topological sorts, so possibly there are faster ones than the one that we used. Okay, so oh, why did it sign me in like that? It signed me into the wrong account. Okay, well, in any case, we are done. That is solution for, what's it called? Course schedule? Yes. Okay, I hope you enjoyed it. Please feel free to like, subscribe, comment, and see you next time.